All right, let's take a look at the American Invitational Mathematics Examination 2022, test number 2, problem number 12. The problem is let a, b, x, and y be real numbers satisfying certain properties. So I'm going to say S is the set of all a, b, x, and y in r to the fourth, such that the properties are a is greater than 4, b is greater than 1, and then this equation is satisfied. X squared over a squared plus y squared over a squared minus 16 equals x minus 20 squared over b squared minus 1 plus y minus 11 squared over b squared equals 1. And the problem is to find the least possible value of a plus b. So in other words, find the minimum over all a, b, x, y in S of a plus b. And this looks like you may want to approach this algebraically. You may want to start moving things around. But when I tried that, I just got quartic polynomials and it just got really bad. So the trick is this is actually a geometry problem. You should recognize that this is the equation of an ellipse. Actually, it's the equation of two ellipses. And a greater than 4 just guarantees that it's an ellipse, and b greater than 1 guarantees the other one is an ellipse, rather than a, hyperbola. So let's just sketch out what these ellipses look like. Here's my x-axis, my y-axis, and the first one will have a center of 0, 0. You should just know the form of the equation, but basically since it doesn't have any minus here, that means the center is going to be 0, 0. So let's draw that in. Goes right there. And it's going to be wider than it is tall, since a squared is larger than a squared minus 16. And the other ellipse will be centered at 20, 11, which is about here, I guess. And this one's going to be slightly taller. That seems good. And the foci, the distance for the first ellipse, the distance from the center to the foci will be square root a squared minus 16, which equals 4. And the distance for the other ellipse will be 1. So we can put focus 1 here at -4, 0, focus 2 at 4, 0, and then for the other ellipse it's going to be taller than it is wide, so its foci will be along a vertical line, and center's at 2011, so 1 down from that will be F3 at 2010. And then up here will be F4 at 2012. Great. And now, what's one important thing that we know about ellipses? You should know that the distance from any point on the ellipse to its foci, or rather the sum of those two distances, should equal twice the length of the major axis. So I'm just going to draw in these distances. And I'll call this point here P. Okay, so we should know that for all, we should know that basically F1P plus F2P equals 2A, and F3P plus F4P equals 2B. For all X, Y, A, B in the space of solutions, we're just going to let P equal X comma Y, so we can say F1P plus F2P equals 2A, and F3P plus F4P equals 2B. And rearranging that, we get A plus B equals 1/2 F1P plus F2P plus F3P plus F4P. So this picture that I drew here, basically for every solution, we're going to be able to take the X and Y from that solution and plot that on this plane here, and we'll get a similar picture. So for a different solution, you might get a point here, and then again, you'll want to connect it to these 4 points to find the value that we're trying to minimize. So really what I want to do is move this point P around in such a way that these 4 line segments are as short as possible. And this is known as, what do you call it? This point, the point P that minimizes that, is called the geometric median. So if you know that, then you might know how to solve this, but if not, you can just kind of tell that you want to move P kind of down and to the right. And actually, once P gets to this point here, where I'm going to draw the intersection of F1, F3 and F2, F4. And I'm going to call this Q. And once you get to that point, the sum of these distances can't get any smaller, because Q is collinear with F1 and F3, so this distance F1 to Q plus F3 to Q is just the distance F1, F3, which by the triangle inequality must be less than or equal to F1 to P plus F3 to P. And then this F2 to F4 must be less than or equal to F2 to P plus F4 to P. So we've sort of found a minimum here, as long as there is a solution that has this point Q. But what does that mean? Let's just write it out in terms of the algebra. We have F1P plus F3P, so this is greater than or equal to 1/2 F1, F3, plus, and then this plus this will be greater than or equal to F2, F4. Awesome. So we found a lower bound for our value A plus B, which we're trying to minimize. But we just need to show that that value can be achieved. And we kind of have an idea that in order to achieve it, we want a solution whose X and Y values are at this point Q. So that means we're going to want the ellipses to intersect this point Q. And we can do that by just choosing an appropriate A and B, because like if it's on this ellipse, for example, then you know this distance plus this distance has to be 2A, because that's the property of an ellipse. So in other words, let's just let A equals 1/2 of F1 to Q plus F2 to Q, and let B equal 1/2 F3 to Q plus F4 to Q. Then we know that it'll satisfy this equation here, but we want to show these inequalities. Well, by again the triangle inequality, we know F1Q plus F2Q is greater than or equal to F1 F2, but it's actually strictly greater since Q does not lie on the line F1 to F2. So we can say A is greater than 1/2 F1 F2, which equals 4. And likewise, B is greater than 1/2. And again, B doesn't lie on the line F3, F4, so it's greater than 1/2 F3, F4, which equals 1. So yes, those inequalities are satisfied, and we can say that A, B, first coordinate of Q, second coordinate of Q is an element of the solution set, and A plus B equals 1/2 the sum of those four distances, which we also know is 1/2 F1 F3 plus F2 F4. Great, so we've shown that for all solutions, A plus B is greater than or equal to this value, and for a particular solution, A plus B is equal to this value. So yes, that is indeed the minimum. We can say min of all A, B, X, Y in the solution set of A plus B equals 1/2 F1 F3 plus F2 F4. And all that's left is to just calculate this value. And I'm going to make myself more room actually. Using the distance formula, we can get 1/2 square root of, now from F1 to F3, the x distance is 24, so 24 squared plus 10 squared. And the distance from F2 to F4 in terms of the x value is 16, so 16 squared plus, and the height is 12, so 12 squared. And let's just figure out what is 24 squared here real quick. 16, 9, 8, 4, we get 6, 7, 5. And let's figure out 16 squared. 36, 9, 6, 1, we get 6, 5, 2. Okay, so this equals 1/2 the square root of 24 squared plus 100, 676, plus the square root of 16 squared plus 12 squared, that's 144. Add that to 16 squared, we get 0. 5, 6, 7, 8, 9, 10, we get 0 and 4, so square root of 400. That equals, let's just do a prime decomposition of 676 here. Take a 2 out, you get 338. Take another 2 out, and you get 169. 169 is 13 squared. So when you take the square root, you're left with 1, 2, and 113. So this equals 1/2 of 26 plus square root of 400 is 20. That's 1/2 of 46, which equals 23. Final answer, 23. Great, thanks for watching.